It's pretty amazing when you think about it. What if the same exact science that lets us figure out the age of ancient skeletons is also the very thing that powers the stars? Well, today we're diving into that incredible story, the story of nuclear energy, from the tiniest atom all the way to the cosmos.
So let's kick things off with a little puzzle. How on earth can scientists look at a skeleton that's been around for 9,000 years and know its age so precisely? And you might think, oh, it's just a good guess, right? But nope, the answer is incredibly scientific.
See, the secret is actually hidden deep inside the atoms themselves. It turns out that every living thing, you, me, this Kennewick man, we all have this sort of natural atomic clock just ticking away inside us. This whole process is called radioactive decay, and it's basically how we can read the story of the past.
So, here's our game plan. First, we're going to look at that atomic clock. Then, we'll dive into how splitting atoms creates, well, an immense amount of power. After that, we'll explore the total opposite, forging a star right here on Earth. And finally, we'll wrap it all up by looking at what this all means for our nuclear future.
All right, first up, the atom's inner clock. Let's really dig into this idea of radioactive decay and figure out exactly how it helped scientists pin down the age of the Kennewick man.
The absolute key concept here is something called half-life. And the best way to think about it is like a perfectly predictable countdown. It's the set amount of time it takes for exactly half of a radioactive substance to break down or decay into something new. And every radioactive element has its own totally unique half-life, ranging from tiny fractions of a second to billions of years. It's incredibly reliable.
Let's see this in action, okay? So imagine we start with 256 milligrams of an element called carbon-15. Its half-life is just 2.5 seconds. So after 2.5 seconds, boom, exactly half of it, 128 milligrams, is left. Wait another 2.5 seconds, and half of that is gone, leaving 64 milligrams, and so on. And notice as the carbon-15 disappears, a new element, nitrogen-15, appears in the exact same amount. It's like a perfect atomic balancing act. And this is how we get back to our 9,000-year-old man. See, all living things, while they're alive, they're constantly taking in a radioactive version of carbon called carbon-14. The moment they die, they stop taking it in, and that inner clock starts ticking. The C14 starts to decay, and it has a half-life of 5,730 years. So by measuring how much C14 is left, compared to other carbon, scientists can calculate the age with amazing accuracy.
Okay, so if atoms can just naturally decay over time, that kind of makes you wonder, right? Could we, force them to break apart and harness all that energy that's released? Well, that is the exact idea behind nuclear fission.
And the key to all of this power, well, it's probably the most famous equation in history, E equals mc squared. What Einstein figured out is that mass and energy are two sides of the same coin. And because c, the speed of light, is such a ridiculously huge number, this little equation tells us that you can turn a tiny, tiny amount of mass into a truly staggering amount of energy.
But wait, where's that mass, the m in the equation, even come from? Well, it's from this really weird but cool concept called mass defect. Think about it like this. If you take an atom apart and weigh all the individual pieces, the protons, the neutrons, their total weight is actually a little bit more than the weight of the fully assembled atom. That tiny bit of missing mass wasn't lost. It was converted into pure energy, the glue that holds the atom's core together. And we call that binding energy.
This is where things get really wild. Fission is all about breaking that atomic bond to get that energy back out. And it works like a set of cosmic dominoes. You fire one single neutron at a big, unstable atom like uranium-235. When it hits, the atom splits apart, releasing a huge burst of energy. But crucially, it also releases a few more neutrons. Those new neutrons then fly out and hit other uranium atoms, which split, releasing more energy and more neutrons, creating a powerful, self-sustaining chain reaction. And look, this isn't just some theory in a textbook. This is a real CANDU nuclear reactor, where that exact chain reaction is happening right now, carefully controlled to generate over half of all the electricity for the entire province of Ontario.
So how does all that actually make electricity? Well, the principle behind it is surprisingly simple. That chain reaction in the reactor core produces an immense amount of heat. That heat is used to boil water into super high-pressure steam. The steam then rushes out and spins a turbine, and that turbine spins a generator that makes electricity. At its heart, a nuclear power plant is just a really, really advanced and powerful way to boil water. Okay, so we've talked about splitting atoms apart, but what if we did the exact opposite? What if we could smash them together? Let's explore the other side of the nuclear coin, the incredible promise of nuclear fusion.
I mean, just look up at the sky. When you see the sun, you are literally looking at the biggest fusion reactor in our entire solar system. It is constantly taking hydrogen atoms and smashing them together to create helium, and in the process, releasing all the energy that powers pretty much all life on Earth.
So, nuclear fusion is just that. It's the process of taking light elements, like hydrogen, and fusing their nuclei together to form something heavier. And here's the kicker. Gram for gram, this process releases even more energy than fission does.
Okay, so if fusion is so much more powerful, why aren't we all using it? Well, the challenges are just immense. To get atoms to fuse, you basically have to recreate the conditions inside a star. We are talking about temperatures that are actually hotter than the core of the sun. At that point, your fuel isn't a solid, liquid, or gas anymore. It becomes a fourth state of matter called plasma. And trying to figure out how to contain that superheated plasma without it just melting anything it touches is one of the biggest engineering puzzles humanity has ever faced. But the reason scientists are pouring their lives into solving this, man, it's incredible. Fusion promises a nearly limitless source of clean energy. The fuel, types of hydrogen, can literally be sourced from water. And the main byproduct isn't long-term radioactive waste, it's helium, the same harmless gas you put in party balloons.
So all of this brings us to our final section, our nuclear future. We've seen the science behind these two incredibly powerful reactions, fission and fusion. So now let's talk about the choice they present to us.
It's pretty clear, right? On one side, we have fission. That's the technology we've actually mastered here on Earth. And on the other, we have fusion, the natural power of the stars that we're still just trying to replicate.
So let's really break down the trade-offs here. Fission relies on heavy, rare fuels like uranium. It creates radioactive waste that lasts for a very long time. But it's a proven technology that works right now. Fusion, on the other hand, would use hydrogen, which is everywhere. It would produce way less problematic waste, but the technology is still totally experimental. We haven't even achieved a self-sustaining reaction yet.
So when you boil it all down, it really comes to this. We have a choice. We can lean into a powerful, proven technology that has known risks we're still figuring out how to manage. Or we can bet on a potential future technology that could be a total game changer, but faces these massive, maybe even insurmountable hurdles.
And really, this is one of humanity's greatest dilemmas, isn't it? Nuclear energy offers us this immense, almost unimaginable power, but it demands an equally immense sense of responsibility. As we look ahead, the real question isn't just about science or engineering. It's about what kind of world we want to create. What choice will we make?